Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a problem on force exerted by a jet of water on a series of radial curve vents. What we have discussed in our last lecture actually. We have derived the equation for a force exerted by a jet of water on a series of radial curve vents. So these derivations are completed in our last lecture. So based on the derivation and formula, we'll solve a problem on this. So here I have taken a question. The jet of water having velocity 30 meter per second strikes a series of radial curve vents. We can see the question, series of radial curve vents, and which is mounted on a wheel, and that is rotating with the RPM of 200. The jet makes an angle of 20 degree with the tangent to wheel at inlet condition and leaves the wheel with a velocity of 5 meter per second at an angle of 130 degree to the tangent to the wheel at outlet. Okay, at the outlet condition to the tangent, it is making an angle. Water is flowing from the outward in a radial direction, that means inward to outward directions, and in the radial direction. The outer and inner radius of this wheel are 0.5 meter and 0.25 meter respectively. That outer radius and inner radius given. Determine the vane angles at inlet condition and outlet condition, work done per unit of water, and efficiency of the wheel. So these are the three things we need to calculate from this question. So first of all, I'll write the data given in this question. So let's write the solution for this problem. So exactly for this concept, I have taken the diagram. You can see here. So this is the center point of the wheel, and the wheel is situated. This is the inner radius of the wheel, and this is the outer one. So inner radius is R2, and the outer radius we have taken here. This is R1. Okay, and this is the velocity triangle for the inlet condition, where we can see that V1, VR2, VF1, VW1, all these velocities are there. And as we know that this is the velocity which is striking the vane, and this is the vane, and this is the wheel actually. So tangent to the wheel is this one at outlet condition, and this is the tangent to the wheel at the inlet condition. And this is the outlet triangle. So this velocity triangle already have discussed many times in our previous lectures. We can see that one. So here we'll just solve the problem. So let's see what are the data are given here. In the first line, you can see velocity of the jet is given. So we can write this is V1 equal to 30 meter per second. Similarly, which strikes a series of radial curves mounted on a wheel which is rotating with a speed of 200 RPM. So here the speed of this wheel is given. So this one we can mark it N. So N is given 200 RPM. Okay, and the jet makes an angle 20 degree to the wheel at inlet condition. So that means this is the jet of the fluid, you can see, which makes an angle of this one. So alpha angle is given here. We can write the angle alpha is given 20 degree at inlet condition, and similarly which leaves the wheel at a velocity of 5 meter per second at an angle of 130 degree to the tangent. So that means which leaves this one. That means this is the leaving part, V2. So V2 here is given, here V2 given 5 meter per second, and the angle we can see, if you see this angle to the tangent to the wheel, that means the angle which is given, this is the tangent part actually. So the velocity which is coming out from this plate, that makes an angle of 130 degree to this tangent. So this is 130 degree. Okay, so we can calculate the beta value here, because this is 180 means this is 130 means, or the opposite angle will be 180 minus 130. So this will be 50. If this is the 50 degree, then in the angle, opposite angles are same in the triangle. If you see, okay, the opposite angles can be equal. So this is 50 means this one also can be taken 50. So we can write next is beta equal to, we can write this is 180 minus 130. So the angle at the outlet condition beta, this one we got here 50 degree. Alpha already is given in the question. This is 20 degree. Next is radius. The radius, inner radius and outer radius are given. So this one also you can write R1. R1 equal to, this is 0.5 meter given, and R2 also given in this question. This is 0.25, half of this meter. And now we can see the angular speed is here. Actually, speed of this wheel is given. Okay, speed of the wheel is given 200 rpm. So we can find out the omega. Omega is the angular speed. So first point, we can calculate the angular speed of the wheel. You can see this is omega. Omega equal to, we know this, you can calculate 2 pi n by, this is 60. So here we can write this is 2 into pi 3.14 into n. N is nothing but 200 divided by 60. So if you cancel this one, so this will be like 3. So 3, this is 3.14. So this will be cancelled, like point something will be there. So near about it will become 20 point some value will come. So otherwise let's calculate this. 20 into 0.14. 2 point, okay, no, not like that. So we'll do one thing. 20 into 1.14. This is wrong. 20 into 3.14 divided by 20. No, divided by 3. Sorry. 20 into 3.14 equal to divided by 3. So 20.93. So this will get 20.93 omega. So omega here unit is, we can write this is radian per second. Okay, now we have calculated omega. So from here again we need to find out, before going to calculate the angle, like Venn angles at inlet and outlet condition. So Venn angle at inlet and outlet condition is nothing but we need to identify theta and phi. Theta and phi we need to calculate. You can see theta is the Venn angle at inlet condition and phi is the Venn angle at the outlet condition. That we can calculate. Now here angular speed I have calculated here. The next task is we need to find out the value of u1 and u2. So these u1 and u2 are the velocity of the Venn at inlet and outlet condition, because this is very simple to calculate. So I can write the Venn velocity, Venn velocity u1, that means at inlet condition. u1 equal to, the formula is there, that is omega r1. So you can write omega equal to 20.93 into r1. This is 0.5. Just half of this we can do it. So this is nothing but 0.47 we can write. 465 will be there. So I am writing 0.47. Similarly, u2 is the Venn velocity at the outlet condition. That is also we can write omega into r2. So omega equal to 20.95 into 0.25. So 0.25 means again half of this. So you can write this one 5. This is 23, or we can write 24. 235 we can write 24. This much meter per second. So these are the basic things, or the, you can say the primary things we need to evaluate first initially before going to the angle calculation for at inlet and outlet condition. Similarly, then based on that we'll calculate the work done and efficiency. So now to calculate the Venn angles, as I told you, Venn angles at inlet condition is theta. This one, this is the Venn angle at inlet condition, and phi is the outlet condition. So to calculate the theta value, which angle we need to consider? We can consider the angle here, ABD angle. In the ABD angle, where the theta value is there, here theta value is there. So theta value we can consider BCD. Okay, we can consider BCD. So by considering, first one I'll write, by considering angle BCD. Okay, here I can write that tan theta equal to, I can write BD by CD value. Okay, I can write in terms of sin theta, then cos theta, then after that I can do sin theta by cos theta. So here I'm directly writing the tan theta value for this triangle. for this triangle here. So what is this tan theta equal to? I can write this is the perpendicular is there, perpendicular divided by the base I can write here. So here VD equal to, actually what is given, VD equal to VF1 we can write. Okay, similarly CD equal to, CD value is not there for us here. Okay, CD value we need to identify. So total length we know, total length equal to VW1. Okay, and from A to C point is U1. So here we can write on place of CD, we can write this is AD minus AC. So again I can write this is VF1 divided by AD equal to what? AD equal to VW1 minus AC equal to E1. Okay, so VW1 is nothing but wheel velocity, this is our flow velocity, and this is the vane velocity you can consider. This terminology already have explained in our derivation time. So here if you see, VF1 also not given and VW1 also not given, E1 is given here. So VF1, what I can write, VF1 and VW1 is the velocity component, is the velocity of jet component in the horizontal direction and vertical direction. This is vertical direction and this is horizontal direction. So I can write here, I'll add one thing, VW1 equal to, I can write in terms of V1, this is cos alpha, and VF1 equal to, similarly I can write this is V1 sin alpha. So V1 equal to how much? V1 already given in the question, this is 30 and this is cos 20, cos 20. Similarly here also V1 is 30 and this is sin 20. This is the only difference we need to find out. So here what I'll do, I'll make it 0, 20 already given, so let's make it sin 20 into 30, 10.26 meter per second. So this one we can write 10.26 meter per second. Similarly cos alpha is there, we can find out immediately. This is 20 degree, go for trigonometry, cos alpha multiply 30 here, 28.19. So VW1 is 28.19 meter per second. So put the value here. Okay, what the value is there? VF1 is 10 point, this is 26, and here in the denominator VW1 minus E1. VW1 how much? 28. E1 equal to how much we have calculated? 10.47. So I'll just deduct this and I'll write directly. This is how much? 28.19 minus 10.47. So this is 17.72. So I can write this is 17.72. So we can write here, this is this much, 10.26 divided by 17.72, 0.579. This is 0.579. So this is actually tan theta. So here if we want to write in terms of theta, then we can write this is tan inverse 0.57 theta. Okay, again we need to solve this one. So again we'll go back to this, go for trigonometry. This is tan inverse of this. So tan inverse of this, if you do, we can get it 30.07. So this is the angle. So one angle we got 30.07. This is the angle theta. This is the vane angle at inlet condition. This is one only we have calculated. Similarly, we need to find out the phi also at the outlet condition phi. At the outlet condition, we need to calculate the phi. Similarly, what I'll do, I'll go for the outlet condition. There also again I'll take the angle, the triangle. What is this triangle is there? EFG. EFG. If you see the triangle here, EFG. So again I can write here by considering the triangle EFG. I can write the tan theta again. Sorry, here tan phi. So tan phi equal to, I can write what was there? Yeah, VF2 divided by the total length actually. So VF2 divided by, I can write this is U2 plus VW2. Again you can consider this one. If you see this part, this is the VR2, if I resolve this component in the horizontal direction and vertical direction, so vertical direction means this one will be there, and horizontal direction means this side. Okay, so this side means this VF2 is nothing, this vertical direction is the same VF2, you can see here, and this is our total velocity component, like relative velocity component in terms of the direction of wind. So that one I can write U2 plus VW2, the total one, horizontal one. Okay, so now if you see, these are the two values which are not given. Again, we need to find out this VF2 and VW2. VW2 also we have not calculated. So here I'll do one thing. I'll calculate the VF2. So VF2 equal to, I can write again V2. Yeah, VF2 equal to what we can write? VF2 sine beta. Why I have written VF2 in terms of V2 sine beta? Because sine beta is given, V2 also given. Okay, so I can write in this way. Okay, no, 10 phi equal to, actually the term is, I've told wrongly. VF, this 10 phi equal to, I need to consider this is this one VF2. That means the base which is there. Okay, if we consider this one, then VF2 into consider here, and with respect to this one, like means perpendicularity by the base. So what is the perpendicularity is there means, then I need to consider this is EF, like EFH. So EFG I told you, here you can do EFH. Okay, yeah, now it is clear. So you can write this is V2 sine beta. If it is G, I have to write, then I need to consider differently, because that is not right angle triangle. I need to find different one. So V2 equal to, we have calculated already, this is already given 5, and beta equal to 50 degree, already we have subtracted this one. Similarly, we need to find out the VW2. VW2 is V2 cos beta. So similarly, here we can write 5 into cos 50 degree. We can find out this value. Yeah, this is 0. What is the angle is there? 50, and cos 50 into 5, 3.21. So 3.21 is this one, 3.21, this much meter per second. Similarly, we can again calculate this. This is 50 degree angle, and sine 50, I hope. Yeah, sine 50 into 5. So 3.83. So both are nearly equally same velocity, 3.83 meter per second. Now just put the value in this equation. So we can get 10 phi equal to VF2, how much? VF2 is 3.83, and divided by U2. U2 already given the, no, U2 we have calculated already actually. The last slide, U2 equal to 5.24. So let's write this 5.24 plus VW2. VW2 how much? 3.21. 3.21. So we can find out finally. This is how we can calculate 3.83 divided, bracket start. Here we can write 5.24 plus 3.21, bracket close, 0.453. So this one I'll write 0.453, and finally phi equal to, I can write what, 10 inverse of this one. So I'll do directly. So go for trigonometry, second, 10 inverse of this, 24.38. So this is 24.38 degree angle. So this is our second answer. Okay, now directly we'll go for the work done. The next part is work done per second. Work done per second by the water. So here the formula is actually, we can write this is rho a v1, bracket start, VW1 U1 plus VW2 U2. Okay, why? Because here beta is taken positive. Okay, because it is less than that one. So we can write this is our formula. But here the question is given, if you see, work done per unit water. Okay, per unit water, unit weight of water actually. Okay, so so work done per unit water also we can calculate, or work done per unit weight, what is given in the question, that also we can calculate. So work done per second this is, and if you calculate the if the question is given in this way, work done per second, okay, per unit weight, actually per unit weight, striking per second. So what will be the formula for this? This also we have actually done. So this is also we have derived in our equation. This is VW1 U1 plus VW2 U2, okay, and divided by the weight of this, weight of water per second. So weight of water per second, weight is nothing but rho V G1 and into G. This is the formula here. Now by cancelling this one, we can get it what? Finally we got actually 1 by G. Actually this is the final formula also. We can write VW1 E1 plus VW2 U2. This is the per unit weight. Now if you solve this one, just we will write 1.91 bracket start. This one we can write 28. Which one? The VW1 28 point something we got there. 28 I remember 19. So 28.19 into E1. Again E1 how much? 10.47. So this is 10.47. Similarly VW2 just now we have calculated. This is 3.214 into 5.23 something is there, okay. U2 value, this one 24. So this one we need to solve it. So finally we'll do one thing, we'll calculate it immediately. 24 is not required. So this is 28.19 into this is 10.47. How much? 294. This is plus bracket start 3.214 into 5.24 bracket close equal 311.99 divided by 9.81. Directly will do 31.80. So this one we got here 31.80. So 80 only we can write. This is Newton per Newton. So this is one answer for the work done per unit weight. The work done per unit weight striking per second. Okay. This is second question what is given. The third question, if you see, the third question you need to identify the efficiency of that. So efficiency of that equation, actually this also we have derived. You can see our previous video lecture there. We can get this one 2 into VW1 U1 plus this is VW2 U2 bracket close divided by V1 square. Actually this is the formula. So yeah, this is our VW1 and E1. Everything is same. If you see this equation and this equation, everything is same. So what I got here, I'll just multiply again to this one and I'll multiply it 2. So it will be simple. So what I want to do, I'll tell you. This one how much I got, just I multiply with 9.81. Then how much? 311 I'll get. So 311 into 2. So how much is there? 623.98. So this is 623.98 divided by V1 square. V1 equal to how much given? 30. So 30 square means this is 900. Okay. So this divided by 900. 0.69. If you see 0.69. So 0.6933. So efficiency equal to, we got 0.6933. And this one again we can write in terms of percentage, that is nothing but 69.33 percentage. This is our required answer. Okay, I hope you understand how to evaluate this. So what are the main terminologies are there? What are the things? We need to remember these formulas actually. So this is our efficiency formula, what we have derived in our last lecture. Similarly, the work done per second by water is nothing but only this one. Okay, but when the question is given work done per unit weight striking per second, then we need to consider the per unit weight we need to consider. So this is per unit weight. If you were confused here, I can write here per unit weight is W equal to, I can write in terms of mg, and this m part is rho v1 and g is here. Okay, so this is about the work done per unit weight. Similarly, these two things we can identify from the velocity triangle itself. Which one? Theta and phi. So I hope you understand this lecture. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box.